So piecewise functions are important because you'll see them in a lot of other classes, but they're not something that that's going to come up again in like the remaining topics that like as part of the remaining topics that we're doing, like a lot of other things we do. We get to practice them throughout the semester because we use them in other things. So piecewise functions we won't use in other topics, and so I'm just going to kind of like bring them back every once in a while so that we don't forget, because they do take a bit of practice. So I don't really think one day is like enough to really get a handle on it. So we'll just kind of talk about them like for 5 minutes every once in a while so that we can like get more comfortable with them. So this one of the sources of confusion that I was seeing on the homework is like whether or not there's an endpoint or an arrow on the left and right side of the graph. So the way that we tell is with these guys. So we have two kinds of endpoints. There's the endpoints. So when we talk about endpoints, we're talking about the endpoints of each individual piece. So there's endpoints where they meet. So that's sort of like your middle endpoint, which kind of sounds funny to call it an endpoint, but it's the endpoint of each individual piece. And then sometimes we have endpoints on the left and the right, and sometimes we have arrows. So if we think about what x values this function is defined for, the smallest x value is -2, which means we're going to have an endpoint here. On the left of our graph. But there is no largest value of x, right? So our x values can go from -2 to 1, so they can't be smaller than -2, and then they can be anything above 1, it tells us on the second line. So there's no biggest value of x. There's nothing limiting how big x can be right there, right? If there was a number here, that would mean we stopped at that number. But because x can be anything bigger than -1, that means we're going to have an arrow on the right. It's not a very good abbreviation for the word right, is it? On the right. So you want to think about if there's a bigger or a biggest and smallest that x can be. So you can almost kind of like try to find the domain before you even start. Like here our domain goes from -2 to 1 and from 1 to infinity, right? Then you have to ask yourself if 1 is included, but that helps us figure out like we have to stop at -2, but we're going all the way up to infinity on the right, so there's an arrow on the right. So because -2 is the lowest x value that I can have, I'm going to start here at -2 because it wouldn't make sense to find any points to the left of -2 because I don't have a formula or a rule for x values that are less than -2. And then I'm going to go up to 1. And then 1 isn't the biggest thing that x can be, right? Because my second rule is defined for all values greater than 1. So if you don't list x values above 1, then you're not going to get any points on that second piece of the graph. Yes?
How many above should we list?
I would do 2 or 3. And then if you don't have enough, you will do more. And what I mean by that is that we know the general shape of these graphs, right? So the general shape of that first piece is what? What's that going to look like? It's a parabola and it's going to open down, right? So it's going to look something like this. And then what about the second one? It's an absolute value, so it's going to be a V. So if I find points and I start plotting them, and that second one doesn't ever become a V, so it doesn't ever turn around. So like if I plot this point and this point and this point, then it looks like that's a straight line. So you have to keep going, like add more points until it turns around so you can see where that point is, where the bottom of your V is. So I always start with like 2 or 3 beyond that middle number of 1. And then if I don't see the shape I know I should see, then I keep going until I see it. So with absolute values in particular, you're looking for your y values to go down, 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 and then turn around and start going up again. That's what tells you that you found the bottom of your v. So our endpoints are -2 and 1. Any other questions, I guess, before I go on, like about like how we know if there's arrows or endpoints at the on left and right? Does that make sense now? How we see that? Okay. And then so I have, why is that not bigger? So I've got an endpoint here and an endpoint here. One other thing I want to mention is that you will never have, the only place you will potentially have something in both columns is at the endpoints. In between, you will never have more than one y value, because then it wouldn't be a function, right? If you have two y values for the same x value, it's not a function. At the endpoints, we do it because we're finding where those open points are. They're not actually points on our graph, but they're points we want to get infinitely close to. Like if we if we stop that first piece at 0, then we would be missing all of the x values between 0 and 1. And so that's why we find a point at 1, even though it's not actually a point on our graph and it's open. But there's no open points in the in-betweens. And so you can only have points for one rule. So you'll always, that's why we put the x's. So you should have an x in one column and numbers in the other. You should never have numbers in both. So for that -2, which line do I see the -2 on?
Just the top function.
Just the top one, which means I'm not going to plug it into the second one. So if I plug -2 into that first rule, I get -6. Is that an open point or a closed point?
Open.
It's open because the inequality between -2 and x is a strict inequality. So far, so good? Okay, so then when the x values are between -2 and 1, oh, go ahead, Anna.
How can you do -2 if it's not equal to?
Right, so we're finding an open point. And what that tells us is our graph is getting infinitely close to the point. So if it was defined for -2, that's where the point would be. But if we started at -1, then we'd be skipping everything between -2 and -1. So we need something to get close to. And so that's why we put a point there even though it's open. Great question. Thank you.
So in theory, is -6 not really the number? It's like -5.999.
Well, so this gets into what we call limits, which is like values that you get closer and closer and closer and closer to, but you never actually reach. So like we would say as you approach -2, the limit of this function is -6, because you get infinitely close to -6 as your x value gets infinitely close to -2, even though that point doesn't actually exist. These are nice functions because they're continuous, like they're like the pieces are all continuous, which means that we can pretend that that point exists, but put an open point there without messing anything up. When you start talking about discontinuous functions, then the limits aren't what they seem like they should be. But in this case, we can like pretend for a minute that the function is defined at -2, find that point, and then say, oh wait, but it has to be open because that point doesn't actually exist.
So there's no limit?
There is a limit. The limit is -6. There's no point. So like when we graph this, there's a point here. So what the limit means is that if I'm walking along here, I will get infinitely close to that point. And so the limit, the thing I'm getting infinitely close to is -6, even though the point -2, -6 doesn't actually exist. So it's like, I've told you guys the football example, right, with the touchdowns. So if you, and this is good to talk about because we're going to talk about asymptotes next week. So you can never end a game on a defensive penalty. So if time runs out and there's a defensive penalty on the play, they always give you like one more play, right? So let's say you're like 10 yards from the end zone and they commit like pass interference on every single play. So every single time you're going to get one more play and you're going to get half the distance to the goal. Will you ever score a touchdown? You won't. I mean, we know in real life, theoretically, somebody could catch the ball, even if there's interference. But pretend you never catch the ball. If there's pass interference on every single play, you will get an infinite number of plays, but every single time you're going to get half the distance to the goal line, right? So you're going to get closer and closer and closer and closer and closer, so the limit is a touchdown. But you can't actually score a touchdown that way, right? You can't actually cross the goal line because you're constantly getting like half. You're always a little bit away. So you get infinitely close to it, but you never actually touch it. So like, you can never actually score, but when we think about it, we're like, oh yeah, eventually you'll get there. Like common sense says eventually we'll get there, right? That's sort of what a limit is like what it should be, but you don't actually get all the way there. Which we will see again when we graph rational functions. Asymptotes do the same thing. They get infinitely close to x values and y values, but they don't actually touch them or cross them. Okay, so what equation or what rule should I use for the x values between -2 and 1? The top one, yes. So I'm going to put an x through the second one so I don't accidentally put numbers there. And then we have -3, -2. And now I'm at another endpoint. Which line do we see that one on? We see it on both, which means I'm going to plug it into both. So this gives me -3. And this gives me, let's see, the absolute value of -2 is +2. That first point on the left, 1, -3, is that going to be open or closed? It'll be open because the inequality on that first line between the x and the 1 is a strict inequality. And what about the second one? It's also open because this is also a strict inequality. And that's okay to have two open points there. We can't have two closed points, right? Because that would mean that I have 2 points or 2 y values corresponding to the same x value, but it's okay to have no y values corresponding to the same x value. So you can have as many open points as you want, but we can't have multiple closed points for the same x value. So then when x is bigger than 1, which rule should I use? The second one. So that gives me, this is 1, 0, 1. Okay, now we're ready to graph. So our first point is -2, 6, then -1, 3, 0, 2, and then we have an open point here, and we know that that's a parabola, so we'll make it look like a parabola. And then the second one, we have an open point at 1, 2, and then point. Oh, I guess I didn't find that one. So then, absolute value functions are the only functions that are not linear that use straight lines. So if it's not an absolute value and it's not a linear function, you should not have straight lines. It should always be a curve. So in this case, it's an absolute value, so we'll have a straight line down to there, and then we have no largest number for x, right? And that's why we're putting an arrow on the right. Is everybody cool with that? Yeah.
So like when you plug those numbers into the second equation
Mm-hmm.
for x, like the absolute value wouldn't like 2 minus 3.
Mm-hmm.
That one, that would be, so it'd be -1.
Right, but the absolute value of -1 is
Always
positive
been,
1.
okay.
Yep. So it's that absolute value. That's why it turns around, because it goes up on both sides. Okay, so what about the domain? What's the domain of this function?
Soft, or parentheses, -2, 1, and then
Mm-hmm.
U1 to infinity. Also.
Very good. So, one thing to keep in mind about the domain is, like, the domain really doesn't have anything to do with the shape of the graph. When we write the domain, what we're saying is that if you pick any number between -2 and 1, or any number between 1 and infinity, there will be some point on your graph that has an x value of that number, right? So if we pick the number 1, there is no point on this graph that has an x value of 1. There's a couple open points, but they're not. Those aren't actual points, right? Those are like holes. They're not actually points on the graph. So that's why 1 is not included. So that's why we have to skip it. The fact that we have 2 intervals in our domain doesn't really have to do with the fact that this is a piecewise function, although you have disconnected intervals more often with piecewise functions because there's more places where you could jump around. But it's because we never hit the number 1. So there's no point on the graph that has an x value of number 1. So, or the number 1. That's why we have to skip it. So what about the range?
Soft bracket -6 to -2.
Mm-hmm.
And then
Is that a hard bracket or a soft bracket? It's hard, yeah. So it's hard because there is a point on my graph that has a y value of -2, which means -2 is in my domain. And then what's next?
-2 to
So are there any points on the graph that correspond to those y values? Right, so we have to start, you're looking at the right point, Emily, but we want the y value. So it's 0, yeah. So 0 to infinity. So again, our range says if you pick any numbers in those intervals, you will be able to find some point on the graph that has a y value corresponding to that number. So there is no point on the graph that has a y value between -2 and 0. That's why we had to skip it. That's why it's not part of our range. And then both those middle ones are hard brackets because there is a point on the graph that has a y value of -2, and there is a point on the graph that has a y value of 0. So both of those have to be part of our range. Any questions? Any questions that came up, as you were doing your homework a couple nights ago? Okay, so I'll answer a question that wasn't asked, because somebody asked it in my last class. It was a really good question. Of like what we would do if there was like a single point or a single y value. So like if we had a point right here. I should make it blue because it's on our graph. So if like we added a point right there, what would that do to your domain?
Doesn't it cover up the hole?
Yeah, it fills in the hole, right? Because now we do have a point that has, or a point that has an x value of 1. And so our domain would become -2 to infinity. What does it do to our range?
Nothing.
0, but it's still covered in
Oh, shit.
to
I need to pick a different point. I keep forgetting about that stupid infinity. I did that last time, too. Let's put it right here. What would that do to my... So it does the same thing to my domain. It fills in that 1. Then what would it do to my range?
make it -1 to infinity instead of 3.
So that's tempting, right? But there's still no
Don't you just add-
points on the graph that are between -1 and 0, right? So like if you have...
add
what were
a
you-
point there in curly brackets?
Yeah, you just put it in. Remember when we first did domain and range and we did graphs like that just had individual points and we just listed the x and y values in the curly brackets? That's what we want to do when we have a single point or even like a horizontal line. So if you have a single y value, you can't describe that with an interval because we're not going from one y value to another y value. It's just one y value, right? So we can't like just extend one of our intervals because there's nothing between -1 and 0, and there's nothing between -2 and -1. So you would just, I mean, technically speaking, you would put it in between, but I really don't care where you put it. It's the same set either way. But that curly bracket means that there's an individual, there's some point that has a y value of -1, but there's no points above or directly above or below it. So that's what you want to do for both single points and also for horizontal lines. So like if I'd have to take this away, but if I did like this, then my range would become -6 to -2, because that bottom part goes from -6 to -2, and then the only other y value is 1. So we would do a curly bracket to add that 1 in. Any other questions? Isn't this fun? These are fun. Okay. Let's do some compositions. So we'll do some more of these. Tomorrow when I give you back your homework, we can talk more about any questions that come up once you look at your homework corrections. Okay, so compositions of functions. So just like combinations, like we did yesterday, compositions are just another way to take two functions and create a third function out of those two functions. We just do it a different way. So if we look at this example, we have two functions here. We have a of x, and the input is what of a of x? What's my input represent? Yeah, the side length. And what's my output? Area. And then my second function, what's the input of that function? Oh, this is... I fixed it on the computer after I printed those. So. It should say 4.99a. Doesn't make much sense if it's just 4.99. So what's the input of my second function? So if I'm calculating the cost of carpeting a square feet, it's a, which represents what? Square feet or area, right? So area is measured in square feet. So A is area. And what's the output? Mm-hmm. So C of A is the cost. And what we're trying to do is write a function. So our new function well, we want it says determine a function for. The thing we're determining a function for is the cost. And so we want the output to be the cost. And then it says of a room with side length x. So that's saying we want the input to be x, which is side length. So we have a function that has the input we want right here, and we have a function that has the output we want, but it's not the same function, right? So we don't have a function that has the input we want and the output we want. But conveniently, the output of the first function is the input of the second one. Those are the same thing. So, if I want to write a new function that takes side length in and gives me cost out, well, I'm going to take my cost function and I want to plug area into that. So we know that a of x is equal to x squared. So the area of a room with side length x is x squared. I'm going to plug that into my cost function. So I'm going to do c of x squared, which gives me, well, the function c just multiplies 499 times its input. So that gives me 499 x squared. So it kind of makes sense. I mean, if you think about it, so if you have a room with side length x, you would be like, okay, the area is x squared, and then multiply that area by 499 to get your total cost, right? So we're just doing that now. This function gives us a way to do that all in one step instead of evaluating one function and then evaluating a second function. So the notation we use for this is c of a of x. So we used a of x, the output of the first function, as the input of our second function. And that's going to be 499 x squared. So this is how we build a composite function. So a composite function is created by using the output of one function as the input of another. So visually, so yesterday, remember, we had like two functions. So we plugged x into both functions individually, got two separate outputs, and then did a sum operation with those two outputs to get our combination function. So to do our composition, we are instead going to start with a single input. We're going to plug that into a single function, which is f. The output of that is going to be f of x. And then we're going to take that and plug it into a second function we'll call g. And the output of that is going to be g of, well, g of whatever the input was. So g of f of x. This is read g of f of x. Lots of f's in there. Should confuse us. So x is the input of f. F of x is the output of f. But it's also the input of g. And then our composite function g of f of x is the output of g. So another notation for g of f of x is, it's like a circle. It's not a dot like multiplication. It's like an open circle of f of x. So what's in the first set of parentheses right here, that's just the symbol for the composition function. So the composition of g and f. And then the input of the composition is x. So when you have a composition, your input is your original input, and then your output is your final output. So the input of our composition function is this, and the output of our composition is this. We're not really going to use that notation. It's sort of going out of style. But you might see it like in the textbook or like in my math lab when you get something wrong and it like pops up a little explanation. You might see that notation, so I just wanted to put it in front of you so you weren't confused when you saw it. It means the same exact thing, but the first one is a little bit more intuitive as far as how you actually find the composition. One thing to notice about these is that they work inside out, right? Our input is X, which is the innermost thing, and then we plug that into F, so we apply F, which is the next most inner thing, and then we apply G. So when we talk about like the first function in a composition, we're not talking about it in terms of like reading left to right. We're talking about the first function that you apply. So in this instance, F is the first function, G is the second function. So you just want to remember you're not going left to right, you're going from inside out. Yes?
So G times X does not or G times X, no, G of X times F of X. It does
Is not
equal.
the same thing. Nope. So that's a great question. So if you have like G of X equals like 2X, and you have F of X equals like X squared, then G of F of X would be, so if you replace F of X with what it's equal to, that's G of X squared, which means multiply X squared by 2. So you get 2X squared. Whereas if you do G times F of X, that is equal to 2X times X squared. I can't make a 2, which is 2X to the third. So with compositions, you're plugging one of the functions into the other function, whereas with combinations, you're just taking the individual outputs and performing operations on them. So let's evaluate some. So this first one we're going to evaluate is F of H of X. So the key to all of these is doing it in like 2 steps. So don't try to think of the whole thing at once. You want to just think of it piece by piece. So you start on the inside. So we're starting with H of X. And we see up here that H of X is equivalent to the square root of X plus 3. So I'm taking F of, and I'm just going to replace H of X with the square root of X plus 3. So now, if I just look at that, it's just saying evaluate F for an input of the square root of X plus 3. So F does 4 times the input plus 2. So I'm going to do 4 times my input plus 2. So just like when we did like difference quotients and stuff, the key to not getting super duper confused in these is to not think of your input as X. Like think of it as your input. Because as soon as we start like getting mixed up in all the X's, it gets really, really confusing, right? So like F of X, or the function F isn't 4X plus 2, it's 4 times your input plus 2, and then you can put any input in there. Because all of these have X's in them, it gets really confusing if we think of F of X, or F as 4X plus 2, because then we've brought an X into it. So you just want to think of it as what it does to its input. So F does 4 times the input plus 2, so if our input is the square root of X plus 3, we do 4 times the square root of X plus 3 plus 2. So next one, so F is our first function, and we see that F is equal to 4X plus 2. So we're going to do g of 4x plus 2. So now the function g of x is input divided by input minus 2. So we're going to do input divided by input minus 2. And that can be simplified, but we're running a little low on time, so I'm not going to actually simplify it. Like you can subtract too, like combine like terms and the whole bit. But that's not really the important part right now. Is everybody good with how we got what we got? Okay, so you guys try h of f of x. Okay, looks like everybody got it. You can't pull a 2 out because 4 isn't a factor of the whole thing. So just leave it like that. Good. Okay, so we all got the square root of 4x plus 5, yeah? I think I saw it on all of them. Okay. I'm going to do one of these. These ones are exactly the same. You just get to simplify your input before you put it into the second function, which is kind of nice. So here we're doing f of, so we're doing g of 4, which is 4 over 4 minus 2. And so you can, but because that's all numbers now, you can simplify that. So you get f of 2. And then you can evaluate f for 2. So 4 times 2 plus 2, and you get 10. So it's the same process. You just get to do a little more simplifying before you have to do the second step. So I want to get to the graphs and the table. So let's skip to that. So again, same idea. We want to do this in 2 steps. So the first thing I'm going to do is figure out what g of 1 is and replace it, right? So I'm just going to replace g of 1 with the y value corresponding to it. So I find an x value of 1, the y value of the point on g is 0. And now my second step is to figure out what f of 0 is. So I find an x value of 0. The point on the graph of f has a y value of 2. So f of 0 is 2. So if I want to evaluate g of f of negative 4, we'll do g of, and then figure out what negative 4 is, or g, so many letters to repeat. Figure out what f of negative 4 is. So we're going to look for an x value of negative 4, the point on the graph of f corresponding to an x value of negative 4 has a y value of negative 2. So I replace f of negative 4 with negative 2. And then I want to find g of negative 2. So I look for an x value of negative 2, and the point on the graph of g has a y value of 1. Again, think of it in 2 steps. If you try to think of it all at once, it gets really confusing because things go from being y values to x values and all that. But once you write f of 0, like on that first one, then you just want to approach f of 0 the same way you would if that was the problem you were given to begin with. So on the table, same idea. We're going to start by replacing g of 1. So we look for an x value of 1. That gives me 0 as an output. And then we want to evaluate f of 0. So we look for an x value of 0. That gives an output of negative 2. Skipping down to D, you can compose functions with themselves. So you can always, like a function just tells you to perform an operation. So you can perform an operation over and over again, right? If I start with x, and I have the squaring function, I can square x and then square that again to get x to the 4th and square it again. So you can apply a function as many times as you want. The approach that we take to evaluating it is exactly the same. So we're going to start by replacing g of 0. So we find 0. That gives me an output of 2. And then I'm going to find 2, and that gives me an output of negative 1. Negative 1. Okay, while I hand out your homework, you guys try the rest. And be sure you write like both steps in this process. This is one of those things on a test that's usually worth like 3 points. And if you just read a graph wrong in one step and you don't show everything, then we have to just take off all the points. But if you show that intermediate step, we can at least give you credit for doing one of the 2 steps correctly. If your final answer is okay. Okay, there's all those answers if you want to check them.